In times past, when we've encountered a number like this, the square root of a negative value, we've said that this is not a real number and we've simply moved on to another problem. Well, with a simple definition here, we can actually create another set of numbers, a set of numbers that is beyond the real numbers that we have been dealing with. All we need to do is define an imaginary unit, I, that is the square root of negative 1. And look at what happens to this problem. Now we have a representation for this problem. We can represent it in a rather special way. The square root of negative 25 can be thought of as the square root of 25 times negative 1. The square root of 25, though, is 5, and the square root of negative 1, by our definition here, is simply I. So we have a way of representing this. Now this is an imaginary number. Now, imaginary numbers fit into our overall number system like this. Now, you recall that the real numbers are composed of rational numbers and irrational numbers. Remember, rational numbers are the numbers that can be written in the form of a fraction. Irrational numbers are the square roots of non-squares, basically, all never-ending, never-repeating decimals. Now, these two sets make up the real numbers. Well, now we have these imaginary numbers that we've just defined, and when we put the imaginary numbers with real numbers that we're already familiar with, we have an enormous set of numbers called complex numbers. Complex numbers are defined as all of the numbers that can be written in the form a plus bi, where a and b are real numbers, and I is the square root of negative 1. Now, this bi is an imaginary number, and the a number is a real number. So complex numbers have a real part and an imaginary part, and that's the reason they're called complex. Not because of some extra complexity, but because they're composed of two different kinds of numbers. Now, we're going to go through operations involving complex numbers, and we're going to add, subtract, multiply, and divide them and just see how those operations work. And they will be pretty much as expected. We treat I as though it were a letter, as though it were a variable. It's not a variable, it's a constant. It's the square root of negative 1. But in terms of performing operations, a lot of times it's handy to think of it like a variable and treat it that way. Here, for example, if we're adding, if we're subtracting these two complex numbers, then we know exactly what we would do, and it would be a pretty trivial situation if this were simply x and x in these positions for I. Well, treat the I in the same way that we treat the x, and we have no problem here. We have, let's see, 4 plus 3i, and then minus understood 1 times all of this, or just a minus sign before the parenthesis changes all the signs. So we have minus 7 plus 2i. And we add the like terms. Well, let's see, the constants, 4 minus 7 is negative 3. And then 3i plus 2i is 5i. So we're adding we're collecting two complex numbers, and we get a complex result. Now, a lot of times it's important to put the answers in problems like this in the form of a complex number so that we can identify distinctly the A and B parts. Now, we've already written this answer in that form. This is the A plus BI form. You see, in other situations, we may have to manipulate a little bit to arrive at this form. Well, here we have a real number, and more specifically, it's an integer that we're collecting with a complex number. And let's see what happens when we collect those. We get, let's see, this is negative 3 plus 5i. Collecting here, the 3's go out, and we have 5i. Gee, 5i is an imaginary number. So it looks like when we collect a real number with a complex number, we could get a purely imaginary number. And actually, all varying combinations will turn out to be true. That we can add different kinds of numbers and end up with a totally different kind of number than we started with. Although this isn't totally different, this is part of the complex number system because it can be written in the form a plus bi, where a is 0. You see, 0 plus 5i. And in fact, all of the numbers that we've ever talked about, all of the real numbers that we've talked about have been part of or a subset of the complex numbers because, a number as simple as, let's say, 3 can be written in complex form as 3 plus 0i. So it's a complex number, you see. Okay, let's go on with some operations. 4i times 5i. Well, multiply numbers times numbers and letters times letters, we have 20i I squared. But remember, I is the square root of negative 1, so really this is 20 times the square root of negative 1 squared, which gives us the radicand. So this is 20 times negative 1, or negative 20. Now, it's a rather important thing to realize that I squared is negative 1. I squared is negative 1. And because it shows up in a lot of problems involving the multiplication of complex numbers. Here we have negative 2i times 3 is negative 6i. And then negative 2i times 4i, negative times positive is negative. 2 times 4, 8. I times I is I squared. But I squared is negative 1. So we have negative 1 times the negative 8, and that gives 8. So we have this. Now, again, we might want to manipulate this and write it in the complex form, which is the a plus bi form. So this would be 8 plus negative 6i, kind of like that. Or maybe like this. There are a few ways of doing this, and you might just refer to the answers in the back of your text to get a feeling for how you may want to write the various complex numbers. We may want it like this, where we have that distinct coefficient of I. Here we're multiplying a couple of complex numbers, and we multiply these as though we were multiplying a binomial, because indeed we are. We use the FOIL method then, so we'll just multiply, let's see, 3 times 5, 15, and I'll put in all of the values and not try to collect the middle term on the fly here. We have 3 times 5, 15, as I say, 3 times negative 4i, negative 12i, and then 2i times 5, 10i, and then 2i times minus 4i is minus 8i squared. So let's see, we have 15, and then minus 12i plus 10i is minus 2i, and the I squared is negative 1, so this term becomes plus 8, and now we can collect the 8 with the 15 to get 23, so this is 23 minus 2i. And again, I could go through another step and say this is 23 plus negative 2 times I if I want to be purely in that complex form. Now, this represents a certain nuance involved with complex numbers. It is often thought that in dealing with radicals, that when you multiply two radicals with the same index, all you need to do is multiply the radicands. So if we follow that idea, then what we would get here would be the square root of negative 5 times negative 10, the square root of 50. But do we really have the square root of 50 here? Well, not exactly. That idea of multiplying radicands when we have the same index works with square roots as long as these radicands are positive. And they've always been positive in the past because we've never encountered this imaginary number idea. So what happens here is this, that this becomes the square root of 5 times I, because we separate the factors here. This is 5 times negative 1 under the radical. So that's the square root of 5 times the square root of negative 1, I. And here, in a similar way, we get 10 times, we get the square root of 10 times I. Now, we would think of it like this. We would think of this as the square root of 5 times the square root of 10 times I times I. That's I squared. I squared is negative 1. So this is the negative of root 5 times root 10 is root 50. And we would simplify this just a little bit further because the square root of 50 contains a square, 25. The square root of 25 gives 5 outside of the radical, and the 2 remains under the radical. So that then becomes our answer. So it's the negative of what we thought we had before, you see, and under that, our other circumstance. So we have to be careful about that when we're dealing with negative numbers under a radical. Take a look at this pattern. As we go through and multiply I as a factor many times, this might be handy. I to the 1 power is simply I. I squared we said is negative 1. I cubed can be rewritten as I squared times I, but I squared is negative 1, so this is nothing but negative I. I to the 4th is I squared times I squared, which means negative 1 times negative 1. Well, that's just 1. Now that's really handy. If I to the fourth is 1, then higher powers on I can be simplified by just kind of subdividing those factors into groups of I to the fourth. For example, if we have something like, let's say I to the 11th, then we can think of this as I to the fourth times I to the fourth times I cubed. So let's see, 4, 8, 11. Yeah, that's right. All right, so we have, let's see, this is 1, that's 1. You see, and then I cubed, we said earlier, is negative I. So all this is negative I. You see, a nice little way to simplify higher powers of I. Well, let's get back to some operations. Suppose we want to square a complex number. Now, the easy way, to deal with this is to think that we have two factors of the binomial and write down those two factors and then use the FOIL method. The fast way in squaring a binomial is to say, okay, in the answer, the first term of the answer is the first term here squared. The middle term is double this product. So it's 2 times 3 times 2i. You see, and the last term is the last term squared, so it would be 2i all squared. Now let's clean up a little bit. We get 9 here, and this product turns out to be 12i. Now the I squared is negative 1 times 2 is just times 4, the 2 squared, you see, is 4, so this becomes negative 4. The 9 minus 4 is 5 plus 12i. Here's an interesting product. It was interesting when we first saw this, where we saw the sum of numbers, the sum of two terms times the difference of the same two terms. When complex numbers are involved, it's particularly interesting as well, because rather than get an answer that is in a complex form, that is in the a plus bi form, where the b value is not 0, you see, a kind of a purely complex number, it has an active imaginary part. Rather than that, we get a real number as the result. Take a look at it. We have, let's see, the sum of terms times the difference of terms means we get the difference of squares. So it's the first term up here squared minus the second term squared. Now when we square this second term, we have, let's see, 2 squared is 4, I squared is negative 1. So this is 4 times negative 1. So it's plus 4. So 9 and 4, 13. So the idea is that we actually end up clearing up that imaginary part, or getting rid of it, when we multiply complex conjugates. These are conjugates, they're also complex conjugates. Now this is a real handy idea when we want to deal with a division problem like this. Now although it's a division problem, it's 5 divided by the complex number, we really treat it like a problem of rationalizing a denominator. We have a radical in a denominator here, really, because this is the square root of negative 1. And we want to rationalize. We want to get rid of that radical in the denominator. So we do that by multiplying by the conjugate of this denominator binomial. And it's the same binomial with a different sign. So we're going to multiply by the conjugate of this binomial over here. But if we multiply by that conjugate in the denominator, we have to multiply by the same value in the numerator. So it's 2 minus 3i up here as well. Now it's helpful for the multiplication process to introduce parentheses around all the binomials. In the numerator we have 5 times 2 minus 3i, that's 10 minus 15i. In the denominator we're multiplying complex conjugates, so we can anticipate that the middle term is going to go out. And we can anticipate that we're going to get a real number for the answer as well. Let's see, we have 2 times 2, or we just think the first term of the binomial squared minus the second term of the binomial squared. And away we go. Let's see, 10 minus 15i in the numerator. In the denominator 4. Now, 3 squared will be 9. The I squared is negative 1. The negative 1 times the negative here, plus. So plus 9. So 10 minus 15i over 13 is our answer. Now if the problem is simpler than this, if we have simply a single item in the denominator involving I, we rationalize by just thinking through it sort of intuitively. We ask ourselves, gee, what additional factor do we need to introduce here in the denominator in order to remove the radical, in order to avoid the I form or remove the I form? Well, all we need is another factor of I, because I squared is -1. So we'll multiply in the denominator by I, and therefore we'll multiply in the numerator by I. Multiplying straight across, in the numerator we have 7I, in the denominator 2I squared, but I squared is -1, so this is 7I over -2, and this minus sign would probably float to the sign of the fraction like this. Let's go through the process one more time involving a binomial. We see here that we have a binomial involving I. We'd like to clear the I from the denominator, so we multiply by the conjugate. The conjugate of 4 minus 2I is 4 plus 2I. So we'll multiply 4 plus 2I into the denominator, and therefore we have to multiply 4 plus 2I into the numerator. And we introduce parentheses around all the binomials, and the tougher multiplication turns out to be in the numerator. I'm going to just use the FOIL method here. 2 times 4, 8. 2 times 2i, 4i. Then 3i times 4, 12i. And 3i times 2i, 6i squared. In the denominator, let's see, we're multiplying complex conjugates, so we get the difference of squares. It's the first term squared minus the second term squared. And we'll come back and clean up a little bit later on that part. Let's see, we have I squared is -1. -1 times 6 is -6. So this is minus 6. Plus 8 is 2. And then for the I terms, 4i plus 12i, 16i. In the denominator, 16. Now, 2 squared is 4. I squared is -1. -1 times minus, or the negative of, the opposite of the -1 will be plus. So this is plus 4. And we'll get 20 in the denominator. I'm noticing a common factor in both numerator and denominator of 2. So I'm going to factor the numerator as 2 times 1 plus 8i. And in the denominator, let's see, 16 and 4, that's 20. And now we have the nice cancellation, 2 into 2, 1, 2 into 20, 10. So we have 1 plus 8i over 10. Now, although it isn't incorrect to write our answer in this form, that is, the form of a single fraction, 1 plus 8i over 10, it's probably a little better to distribute the 10 through the numerator and write this in purely complex form, that is, as 1/10 plus 8i over 10. And then in this fraction we have an additional reduction that's possible. So we have 1/10 plus, let's see, the 2 into 8, 4, 2 into 10, 5. So we have 4i over 5. And further, we would probably write a distinct coefficient of I over here and write this then as 1/10 plus 4/5 I as the final answer. Recall from our discussion just a few moments ago that when we multiply the square root of one negative number times the square root of another negative number, that we need to use the I form in order to evaluate properly. This is the square root of 3 times I. This is the square root of 12 times I. The square root of 3 times the square root of 12 is the square root of 36. I times I is I squared. Now I squared is -1 and the square root of 36 is 6, so -6 is the answer to this, or the simplification of this expression. Here we have a quadratic equation that we'd like to solve. We might try to solve it by factoring to begin with. We find that it's unfactorable, so we would probably go right into the quadratic formula. Now, one thing that we can do in introducing the quadratic formula is that we can discover the kind of answer that we're going to get, the kind of solution, or the set from which the solution will emerge, whether it's a rational number or a single rational number, two rational numbers, an irrational number, or in this case, a complex number. And we can identify that by evaluating the value of the discriminant, the b squared minus 4ac, We notice here that the a value is 3, the b value -2, and c is 5. So for b squared minus 4ac, we replace b with -2, replace a with 3, and c with 5, and performing operations we find the discriminant to be -56. Since the -56 occurs under the radical, we know that we're going to get an imaginary number here, and therefore our solutions will be complex. And complex solutions of quadratic equations always occur in conjugate pairs, as we'll see here in just a moment. All right, so we write down our formula, we replace within the formula and evaluate. This is the square root of -56, which we'd like to simplify a bit. Now, 4 is contained in 56. Now, just as a reminder, this is the square root of -56. Now, I have factored it here in the next step, that -56 can be thought of as 4 times 14 times -1. Now, I'm sort of skipping over the other parts of this. It's rather trivial to have the opposite of -2 to give 2 and 2 times 3 to give 6 in the denominator, but so all the action is right here. The square root of 4 gives 2 outside of the radical, the 14 remains under the radical, and the square root of -1 is I. So we would write all of that like this. Now the 6 divides both parts of our numerator, so we would probably write separate fractions here, and these are those separate fractions, and now we can see the cancellation opportunities. 2/6 becomes 1/3, and this 2 cancels with the 6, leaving a 3 in the denominator. And if we want to write a distinct coefficient of I, we would write this fraction, this part, as the square root of 14 over 3. You see, as the distinct coefficient for I. So these then are our two answers in the complex form. Notice that they are complex conjugates here.